Hello, I'm Seraphim. I'm presenting my analysis of hospital bed occupancy forecasting using time series. I evaluated 5 different forecasting approaches on nearly 4 years of hospital data, and I'll share which methods work best and why, with some surprising findings about model complexity. Hospital capacity planning is a high-stakes balancing act. Get it wrong in either direction, and there are serious consequences. Understaffing puts patients at risk. It leads to inadequate nurse-to-patient ratios, delayed care, and staff burnout. But overstaffing wastes money. Staffing nurses represents about 25% of a hospital's operating budget. The COVID-19 pandemic was a wake-up call. Hospitals worldwide faced unprecedented demands that overwhelmed capacity. It proved that hospitals need robust forecasting systems, not reactive crisis management. I analyzed data from Advent Health Orlando, a major health hospital system in Central Florida. It was one of the busiest hospitals in the broader hospital capacity data from the Department of Health and Human Services. The data spans 197 weeks from July 2020 through April 2024, covering the full arc of the pandemic and return to normal operations. Average bed occupancy is around 2,200 beds. To test whether external factors improve forecasting, I also incorporated CDC flu data and NOAA weather data for the Orlando area. As you can see in this time series, there's a clear structure, seasonal patterns, and an overall trend. The question is, can we model this effectively? Exploratory data analysis revealed something important. Hospital bed occupancy has very strong annual seasonality. It is evident in our seasonal naive baseline, which simply uses bed occupancy from the same week 1 year ago. It achieves remarkable accuracy for its simplicity, even outperforming some of our more complex models. This finding foreshadows our results. If seasonality is strong, simple seasonal models might perform surprisingly well. I evaluated 5 models spanning the full spectrum of forecasting approaches. Starting simple, the seasonal naive baseline just uses the same week from last year. It's our benchmark. The sophisticated models can't beat this. They're not adding any value. The SARI-MAX model is a seasonal ARIMA with external regressors like flu rates and weather. This structural state space model explicitly decomposes the series into trend and seasonality using a Kalman filter. The VAR model tests whether modeling bed capacity jointly with COVID patient percentage improves forecasts. And the LSTM is a deep learning model that can capture non-linear patterns. The question is, does more complexity mean better forecasts? Rather than a single static forecast, I evaluated models using rolling forecasts with adaptive retraining, simulating how these models would actually perform in production. The data was split 80-20, 157 weeks for training and 40 for testing. During the test period, models generate 4-week forecasts, then advance forward, incorporating actual observations. Most of the models retrain every 2 weeks or sooner if forecast errors spike. This approach tests whether models can adapt to changing patterns, exactly what a hospital operations team would need. Here are the results. First, the good news. All models achieve between 1 and 3% mean absolute error. That seems to be decent for hospital operations. It means that the models have typical forecast errors of around 40 to 70 beds out of around 2,200. The structural state space model performs the best with 1.75% MAE and a near zero bias. That means it doesn't systematically over or under predict. But here's a surprise. The simple seasonal naive baseline, just using same week last year, achieves about 1.81%. That's only 0.06 percentage points worse than the best model. The LSTM comes third, SARI-MAX fourth, And VAR, the multivariate approach, performs the worst with the highest error and largest bias. But with further hyperparameter tuning and feature selection, the model has the potential to do better. These results tell us something important about this data. There are 4 key insights we can gain from this analysis. First, strong seasonality dominates. Hospital occupancy follows such stable annual patterns that same week last year is a remarkably good heuristic. Second, the structural model performs best because it directly models what matters, trend and 52-week seasonality. The Kalman filter is perfectly suited for this. Third, and this is important, complexity doesn't guarantee accuracy. The VAR model, despite its theoretical justification, and the LSTM, with all its deep learning power, couldn't beat classical methods. Fourth, external factors like flu rates provide only modest improvement for this particular data. This seasonal signal already captures most of what they would tell us. So what does this mean for hospital operations? In the hospital setting, we can deploy a structural state space model that retrains periodically with relatively low error and near zero bias. This enables nurse scheduling 2 to 8 weeks in advance, resource planning, budget forecasting, and early alerts for high occupancy weeks. We can always use the seasonal naive baseline as a sanity check. If your fancy model suddenly diverges significantly from same week last year, there might be an issue. The baseline isn't just a benchmark, it's a useful monitoring tool. And sometimes if we don't want to run fancy models, we can just take a look at what happened at the same time last year. So remember this the next time you're building a data model. The key to good forecasting isn't always more complex or sophisticated algorithms. It's understanding your data's fundamental patterns. For this particular hospital data, that pattern is strong, stable, annual seasonality. I plan to continue developing this project. Future work includes exploring additional features such as emergency department admissions, testing ensemble methods, and refactoring the codebase into a production-ready pipeline with automated data ingestion and model retraining. If you're interested in the code, I'll soon put a link in the description. Thank you all for watching and have a great day.